So we've developed conceptual machinery to essentially create a way for characterizing heat exchangers. And now it makes sense to try to use that conceptual machinery to solve problems where maybe we know the properties or some properties of a heat exchanger system, but we don't know others, and we want to use the equations that we've created to find them. So here is a classic example of such a system, a relatively rudimentary, like simple one, mind you, nevertheless instructive. So here's the setup. This is a double pipe counterflow heat exchanger. Double pipe because it's basically just one pipe inside of the other. So about as simple as you can get for a design of a heat exchanger. And it's counterflow because the two liquids inside of this heat exchanger, the cold water and the hot water, as labeled here, are flowing in opposite directions. And that really only matters from the perspective of the calculations that we're going to do, both for relating NTUs to efficiencies and heat capacity ratios, as well as whether or not we need a correction factor for calculating the heat transfer rate through the heat exchanger using that delta TLM equation that we saw before. But the point is, this is a counterflow heat exchanger because of the way that it's set up, right, physically, that the liquids are flowing opposite to each other. And in this counterflow heat exchanger, cold water comes in with a mass flow rate of 1.2 kilograms per second. And at its inlet is at a temperature of 20 degrees Celsius and exits at a temperature of 80 degrees Celsius, all right? The hot water comes in from the other side and enters at a temperature of 160 degrees Celsius, but we don't necessarily know at what temperature it exits. And it flows in at a rate of 2 kilograms per second. Now we can find in tables that the approximate specific heat capacity of both of these waters, right, the hot water and the cold water, is approximately these. And remember that there's a variation in what that specific heat capacity is as a result of the fact that the temperatures are different, right? So these are the same substance, right? Hot water and cold water are still water. But the fact that one of them is at a higher temperature than the other means that the specific heat capacity is going to be slightly different. Be aware, right? We're being a little bit sloppy with this because there isn't just a single specific heat capacity, right? That specific heat capacity for either the hot or cold liquid is going to change as the temperature of the liquid changes through the heat exchanger. But these are approximately representative values at either average temperatures or the temperature that we have available to us for those liquids in this problem. And we assume that the error that is associated with our calculations based off of this assumption, that error is either negligible or factored in to the certainty that we have for whatever it is that we're calculating, right? So we have these specific heat capacities. We have the mass flow rates. That's great because it lets us calculate the heat capacity, or I should say the heat capacity rate ratios. That lets us find what those things are, okay? And that'll be important because it'll give us information for how to solve this problem using NTUs and using efficiencies. We know a couple of other things too. We know, for example, that the diameter of the central pipe of that, pipe carrying the cold water is 1.5 centimeters. We also know, or have been told, that the overall or average, or whatever you want to call it, heat transfer coefficient, the U value of this heat exchanger is 640 watts per meter squared degree Celsius difference, or watts per meter squared Kelvin, however you prefer to phrase it. And so given this information, we can ask ourselves, what is the length of this heat exchanger? So this is kind of an unorthodox question from the perspective of what we usually do for heat transfer. Usually we're trying to look for heat transfer coefficients, or we're trying to look for heat transfer rates. But in this case, we're actually trying to create a design parameter, so to speak. Like hypothetically speaking, you can imagine that, maybe we have that this is the setup for a heat exchanger that we would like a heat exchanger to heat up water from 20 degrees Celsius to 80 degrees Celsius, and that it satisfies all of these properties or parameters or what have you, And then we're just trying to design the length such that this works the way that we want it to, right? And of course, we will have to use calculations that involve heat transfer rates in an interesting, clever way. So how do we do it? Well, the first thing that we can ask ourselves here is, what is the simplest calculation that we can do for heat exchanger problems? And do we have enough information to do it? My recommendation always, whenever you see a heat exchanger problem, is to ask yourself, can I find the heat transfer rate through the heat exchanger? Is that available to me given the information I have? And the answer for this problem is yes. What is the actual expression? Well, remember, we have the golden rule, which we had first encountered when talking about internal flow, but now we can actually deal with from the context of working with heat exchangers. And all that the golden rule says is that Q, right, the net heat transfer rate through the heat exchanger, is equal to the mass flow rate of one of the liquids times the specific heat capacity of one of those liquids times the temperature difference between the inlet and the outlet of that liquid. Now, I'm being deliberately ambiguous about what this delta T is, because in order to get a positive value for this, it actually depends on whether or not we're using the cool liquid or the hot liquid, right? So what information do we have for which of these liquids can we calculate this Q for? Well, we can't do it for the hot liquid, at least not yet, because even though we know it comes in at 160, we don't know at what temperature it exits. So we don't have this delta T. For the cold liquid, however, we do. And so as a result, all we have to do is just say that this is for the cold liquid, and that this delta T, once again trying to make sure that we get a positive number, that this delta T is just the difference in the temperature of the cold liquid at the outlet minus the temperature of the cold liquid at the inlet. Okay? Once again, this is just to try to make sure that we get a number that's positive. And so this is 60 degrees Celsius. This mass flow rate is 1.2 kilograms per second. And this specific heat capacity is just 4,180 joules per kilogram degree Celsius. So given that this is the case, we just have to multiply. And when we do the actual multiplication, skipping, actually writing down the values, we wind up getting that the net heat transfer rate through this heat exchanger is about 301,000 watts. There we go. All right, so it's just multiplication. So this now tells us a key piece of information about how this heat exchanger works. We know that no matter what this outlet temperature is, we can already figure out that the heat transfer rate through this heat exchanger is 301,000 watts, which is great. Okay, can we use this information to find something else about the state of this heat exchanger? And the answer is yes, because we can use that same golden rule to try to figure out the temperature of the hot liquid at the outlet. Remember that equation that I wrote down earlier is valid for both the hot liquid and the cold liquid. We have to, change the mass flow rates and the specific heat capacities, and we might have to change the order of the temperatures in the delta T, but it nevertheless works. And so we can find that the Q that is arriving into the cold liquid from the hot liquid is the same, of course, as the Q that leaves the hot liquid. And so we can now write this down in the following form. And so because we know these mass flow rates and specific heat capacities, because we know them for both of the liquids, we know this inlet temperature, and we found the Q from our previous calculation, we can therefore find the outlet hot temperature, THO. And once again, plugging in numbers and skipping the actual calculation, we'll wind up getting that outlet temperature is about 125 degrees Celsius. that gives us all of the temperature information that we need for this problem. We can just write it down over here, make sure that we remember it. And the reason that this is super useful is because now we can use this temperature information to calculate something about the design of this heat exchanger. Now, the golden rule is very easy to use, as you just saw, right? It's a very practical way of developing information about temperatures. But the challenge about it is that it doesn't say anything about the geometry of the heat exchanger itself. We need some other equations to be able to do that. What equation have we developed for heat exchangers that tells us something about the geometry? Well, here's one. Q is equal to U times AS times delta TLM. Right? So this is the equation we had constructed previously. This surface area over which the heat transfer takes place is effectively the surface area of this little pipe right here. Okay, right? It's a curved portion of the surface area of that small central pipe. That surface area is a function of the length of the heat exchanger. And so hypothetically speaking, if we can find what the surface area is, then we'll be able to find precisely what the length of the heat exchanger should be. So do we have enough information to find that using this equation? Take a look. We know the Q, right? This is the same Q that we calculated at the first step. This delta TLM we can find as a result of the temperatures, of having all four temperatures in this system. The U we have been given as a result of just whatever evaluation has been performed on the heat exchanger previously, right? We just were given that this is 640 watts per meter squared degree Celsius difference. And so all we have to do now is just solve for that surface area. Or more precisely, we have to find the delta TLM. So how do we calculate delta TLM? Well, we talked about this in the previous lecture, but let's just do it again, just in case. The only way that we have to worry about constructing this in any way that's different from, say, in the bare bones internal flow case is that we create labels for each end of the heat exchanger. We say, well, maybe this is end 1, and then maybe we say this is end 2. And then we write down delta TLM as the difference in temperatures in location 2 minus the difference in temperatures in location 1 divided by the logarithm of the ratio of those differences. So, like this. Now, this delta T2 is just the difference in temperature between the hot liquid at 2 and the cold liquid at 2. So this number is 80 or negative 80. It actually doesn't matter which way you define the difference, right? It'll all work itself out in the end. Over here, right, following the same convention, right, you want to make sure that if you define the delta T as hot liquid minus cold liquid, you have to follow the same idea, right? So 160 minus 80, that's my delta T2. And my delta T1 is 125 minus 20. So you just plug in those values in here, and then you wind up getting a delta TLM. Now, one hint as to whether or not you've done this correctly is that you should find that the number that you get is somewhere between the temperature difference here and the temperature difference here. So for example, the temperature difference here is about 105 degrees Celsius. The temperature difference here is about 80 degrees Celsius. So we should get something that's in between. It shouldn't be the average, because this is not an average. You should get something that's just in between. And if you actually plug in the numbers that I just mentioned, the number that you will eventually get, I'm just checking with my notes to make sure that I write it down correctly, the number you wind up pulling is approximately 91.9 degrees Celsius difference, I suppose. And so we get that answer. Now that we have this delta TLM, we have the Q, we have the U, all we have to do is to solve for the surface area, right? This is simple algebraic manipulation. So if you do this, we wind up obtaining that the surface area, once again, avoiding the manipulation, is approximately 5.12 meters squared. All right? And so this 5.12 meters squared tells me what this surface area here is. Okay? So given that we have this, can we find the actual value of the length of the heat exchanger? Of course. Right? Now, what is this surface area? Well, we had talked about it being for a duct, right, with constant cross-sectional area. We talked about the fact that the curved portion of the surface area is just the perimeter times the length, right? The perimeter of the cross-sectional area times the length of the tube. So this AS is really just P times L. And because this is just a circular duct, this winds up being pi times that diameter times L. Okay? And we know the diameter. Obviously, we know pi. We know the surface area. And so now we can calculate the L. And so solving for the L in this calculation, we wind up getting, pardon me, that L is a very long 109 meters. So suspiciously long, but still, that's just what it is. And so we have a number. The exercise is technically over. We've already figured out all the properties we need to find, but we may also then go in and say, well, can we not find this another way? Like, what if, rather than necessarily using the method we just used now, where we calculated a log mean temperature difference, can we maybe use that notion of NTUs and its connection to effectiveness and heat capacity ratios, or heat capacity rate ratios, I guess, to determine this length? Like, can we do that? And the answer is yes, we can. So I'm going to basically wind the clocks back and see if we can't find it via this other method. Now, one thing that you should know is that whenever you're trying to work with an NTU effectiveness approach, you always have to make sure that you have some sort of correlation or equation that tells you what the NTUs are as a function of the effectiveness and the heat capacity rate ratios. This is the equation that you would find for a double pipe counterflow heat exchanger in most standard heat transfer textbooks. Of course, this equation changes if the geometry of the heat exchanger changes, all right? In fact, the only reason that we were able to do the method that we just did was because the geometry of this was so simple that we could model this as a straightforward counterflow heat exchanger and define these locations. If this had been like a crossflow heat exchanger, all hell breaks loose. Either way, this is the equation that we're going to use. Now, first things first, can we calculate the heat capacity rate ratios? Sure. We have the specific heat capacities, we have the mass flow rates. We can just calculate these things, figure out which one's the minimum, and divide it by the other one. So what are those values? Like, what do we wind up getting? Well, the minimum heat capacity ratio, it turns out, when you actually perform the calculation, is the one for the cold liquid, right? So if I multiply the mass flow rate of the cold liquid by the specific heat capacity of the cold liquid, I would wind up getting something that has units of approximately, not units, I'm sorry, it would have a value of approximately 5,020 watts per degree Celsius difference, okay? And this is the smallest one, of course, because the largest one, if I were to actually write it down, would be the one for the hot liquid, which evaluates out to be approximately 8,620 watts per degree Celsius. Okay, so This one is the heat capacity rate for the cold liquid, and this one is the heat capacity rate for the hot liquid. And there's no thing that would have been able to tell us what those numbers were before we actually did the calculation. I just know what they were because I have it written down in my notes. But we would calculate both of these, detect that this is the smallest one, and then off I go. All right, so these are the numbers. And this immediately tells me what this C dot R is, that ratio. All right, so if we calculate what that ratio is, this is approximately 0.582. All right, so now that we have these numbers, we know that this is going to be useful because it gets used directly in the equation for calculating NTUs. But nevertheless, we now have to ask ourselves, how do we calculate the effectiveness of the heat exchanger? Well, remember what the effectiveness is. Right? The effectiveness is supposed to be a measure of the actual performance of the heat exchanger relative to some theoretical maximum. Okay, and so the way that we calculate what that is by defining an epsilon. Where we have the actual Q of the heat exchanger being divided by this hypothetical maximum. Now, how do we actually get a number out of this? Well, we already know the Q. We got it from the golden rule. So that part's done. How do we get this Q max? Well, we had written down an expression for it. We had said that the Q max was actually just the smallest heat capacity rate, so this minimum C dot, multiplied by the difference in temperatures between the hot liquid at the inlet and the cold liquid at the inlet. So what are those temperatures? 160 for the hot liquid and 20 for the cold liquid. So this is just THI minus TCI. We know this number. We just calculated it. We know these two numbers. In fact, we knew them from the start, right? Because this isn't the outlet temperature, this is the inlet temperature. And we calculated the Q using the golden rule. So now, pardon me, and so now we can calculate the effectiveness, all right? If I plug in numbers over here, pardon me. If I plug in numbers over here, the effectiveness that I would wind up calculating is approximately 0.428. And remember that this doesn't have units, just like the heat capacity rate ratio, because of the fact that these are dimensionless quantities, which was the whole point. And so now that we have this effectiveness, now that we have the heat capacity rate ratio, all we have to do is just plug this in and calculate the NTU. And if we evaluate that expression, what we would wind up getting for the values that we just found is approximately 0.651. So there we go. Once again, dimensionless. So we have this. Why on earth is this useful for determining the length of the heat exchanger? Well, remember how the NTU of a heat exchanger is defined. It's supposed to be the U value of the heat exchanger multiplied by the surface area divided by that minimum rate. Okay? We know NTU, we know U, we know this minimum rate, and hypothetically speaking, we wouldn't know what the surface area is. So that's what we'd use. And so what would happen, simply enough, is that we just say, okay, plug this in, plug this in, plug this in, calculate that surface area, and then calculate the length from the surface area using exactly the same process that we did previously. So unsurprisingly, if we actually tried to solve for the area using these numbers, the numbers that you wind up getting are basically the same. Just for confirmation's sake, we'd get that this would be approximately 5.11 meters squared. That's what I got when I tried to analyze this, using the second method, and then converting this into a length, the number I eventually get is 108 meters, which is virtually identical. It's within 1% error of the same number that I tried to pull in before. And so you can see that, assuming that we have enough information, there's two different ways to go about heat exchanger problems. We can either rely on correlations that connect dimensionless quantities inside of them, which we will often have to do whenever we don't have the ability to set up a problem in the diagrammatic way that I did just now, or we can use kind of the delta TLM method, where we calculate a log mean temperature difference, and then we relate the heat transfer rate through the heat exchanger to the actual, to the overall heat transfer coefficient and the surface area and that sort of thing. Now, as a reminder, if this had not been a counterflow heat exchanger, if this had had some much more complicated geometry, we would have needed to include a correction factor inside of that delta TLM equation that we saw previously. That correction factor is 1 whenever we have a counterflow heat exchanger, but if this was a crossflow heat exchanger, the workflow is to basically pretend like it's a counterflow heat exchanger and then just multiply U times AS times delta TLM with a correction factor F to get the actual heat transfer rate Q. Everything else follows in the exact same way. And so this tells us everything that we need to know, or at least most of the practical paths that we can take in order to calculate the properties of heat exchangers, right? And having spent so much time talking about systems that are governed by convection, and earlier having spent so much time talking about systems that are governed by conduction, we now have to look, as one of the final subjects of this course, we have to look at the third mysterious form of heat transfer that we hypothesized way back when we started these lectures. And that form is radiation, which will be the subject of our next lecture.